Alright, in an earlier video, I derived the shell theorem for you. And what you probably felt watching that derivation was that it was really complicated and there was a lot going on. So what I'd like to do in this video is take a step back, since it's probably been a little bit of time since you watched that one, and hit some of the key points. So just summarize what was important from that, both in terms of how I approached the problem and also what the theorem itself says, which we didn't have a chance to discuss at that time. So first of all, in terms of the setup of the problem, there were a few parts that will keep coming up in various contexts as we do more integrals of the same sort this quarter. Okay, so one of the key things that we did right away was we started with a detailed diagram. And drawing a detailed diagram is almost always going to be a really important first step, because that sets you up to avoid confusion. It sets you up to identify what parts you need to work on as you go, and so on. All right, so it's just a really good basis for doing an integral. Okay, so once you had a detailed diagram, we also wanted to come up with lots of labels. So we had to label both known quantities as well as variables. Okay, so in the shell theorem, some of the known quantities were the radius of the planet, the mass of the object, and so on. And so as we move forward and consider more situations, we will still want to label what we know, and also give names to some of the things that we don't know, like the distance between a point and the mass element, or the angle of a particular mass element relative to the origin, and so on. So we may have to label many different variables in each problem. Okay. We also need to decide how we're going to split a shape into elements. Okay, and there may be a lot of ways to do that. So decide how we will split up shape. For instance, in the shell theorem, we started out by splitting a sphere into shells, and we decided that a shell would be easier to approach. And then we split up the shell into rings, and then we split each ring into little elements. That's not the only way you could try to solve that problem. You could split it into small elements that each have a certain x, y, and z, little cubes. Or you could try to split it up into cylindrical shells if you wanted to. There are a ton of different ways you could approach it. So which exact way you split up a shape will depend on what the shape is. Some will be easier than others, as we will see. Okay. We also needed to find relationships between the variables. So there were a couple of different ways that looked in the shell theorem. So one is we used sines and cosines in order to relate angles and lengths together. So the ordinary thing that we do in physics, where we have right triangles, we used those as well. We also had to be a little more clever, and we used the law of cosines. So things like the law of sines, the law of cosines, those can be useful tools here. We also took a derivative of an expression with one variable relative to another variable, and we found that to be useful as well. So at this point, taking advantage of the large number of mathematical tools that you have at your disposal is going to be really helpful. Another thing that we did is we converted it into a density. So we used the idea of density to relate mass to area. Okay, and that was important in the case of the shell theorem because mass is what was related to the force. So that was the thing that we needed for doing the physics. But area was the thing that we could calculate with the integral. So by using the concept of density, we could relate those two things and build up the integral that way. And then finally, we used symmetry to argue which direction the force would ultimately end up. And we're going to talk more about symmetry in upcoming chapters. So symmetry is going to stick around for the whole course. In fact, if you became a professional physicist, symmetry would stick around for your entire life. Symmetry is a concept that shows up over and over and gets increasingly abstract the further you go into physics. But we will come back to that later. But for us, the thing that symmetry really helped with is we could identify which direction the force would be, and that made it so we only had to calculate one component of the force. We did not have to worry about whether there were going to be components in some other direction because we knew they had to cancel out. Okay, so those are some of the key things that showed up in terms of the setup. I would also like to talk about the theorems themselves. Okay, so for the theorems, there are in fact two shell theorems. So the one that I solved is the one for having the object, the point-like object, outside the shell. So here is your shell. Try to draw it kind of thin. Okay, so the first shell theorem, which I'll do in blue, is that if I have an object out here, then it is calculated as if we use Newton's law of universal gravitation. So this is mass of the planet, mass of the object, over this distance squared. And we can treat the shell as if it were concentrated at its center. Okay, that's the big takeaway, and it's a really, kind of beautiful result of Newton's law of universal gravitation. So that's really useful. It tells us that anywhere outside a spherical shell, that's true. And if we assume that a planet is built out of spherical shells, even if there are some really heavy spherical shells at the center, maybe the planet has a dense core, there are outer spherical shells that may be like layers of liquids or gases. Each shell will individually behave like a point at the center, and so when we add those all together, the whole sphere will also do that. Okay. The second shell theorem actually tells us what happens if we have an object inside the spherical shell. And the surprising result here is that for that object, the force from the shell is equal to 0. So if a point is inside a uniform spherical shell, we can ignore any shell outside that point completely. Okay, so in order to derive that, it's actually almost exactly the same as the theorem that I did in class. The only difference would show up when we put in the limits of integration. One of the limits of integration would look slightly different, and instead of getting 4RE for the integral, you get 0 for the value of the integral, and it happens to cancel out exactly. Okay. So that's really nice too. If we have some sort of spherical planet and you want to consider the force of gravity somewhere inside the planet, you can ignore any mass that is at a larger radius from the center than the point we are interested in. Okay, so for instance here I could draw something kind of like this. Any mass outside of that would not count towards the force of gravity on that point. Any mass that was inside that dotted line would act like a point at the center of that planet. Okay, so as you would get deeper and deeper into a planet, the force of gravity would get smaller and smaller. So one kind of interesting sci-fi application for this theorem is called a Dyson sphere. And the idea here is you would take for a sufficiently advanced civilization, you could take the sun or whatever star, and instead of just building, solar panels on a planet, like you might do to collect solar energy, you could in fact build a whole ring around the star. Or, if you got advanced enough, you could build a whole sphere around the star and completely enclose the star and capture all of the energy that it produces. Okay, and that's called a Dyson sphere. All right, so what the shell theorem tells us is that the force on the star by that Dyson sphere is 0. The force on the star by the Dyson sphere equals 0. And by Newton's third law, the force the Dyson sphere by the star is also equal to 0. Those have to be equal and opposite to each other. So, in fact, a Dyson sphere would be inherently unstable. If you tried to enclose a star by some rigid structure, if the structure started to drift ever so slightly, let's say it drifted, to the right a little bit, it would just keep on drifting because the star would not be able to pull it back into alignment. And so this would not actually work out in practice. You'd have to come up with some more clever way to do this. Okay, so it's just kind of a fun example.